All right. We've looked at infinite limits. Now let's look at some limits at infinity. All right. So our infinite limits, whenever I approached a specific value and my answer was infinity, those were vertical asymptotes. Now, whenever I look at limits at infinity, we're going to have horizontal asymptotes. So limits at infinity and horizontal asymptotes. All right, so that's what we're looking at. So what this means is I'm going to take my limit as x approaches infinity of whatever it is that I'm taking my limit of. And that is going to be L. So the difference here is the fact that x is going to approach infinity. That's what a limit at infinity means. So I'm approaching infinity and then I get L, which tells me then at that point I have a horizontal asymptote at y equals L. That's my horizontal asymptote. By that same rationale, what if I go in the other direction? I can also have the limit as x approaches negative infinity of my function, and that's equal to m. You can also have a horizontal asymptote at y is equal to m. All right. So you can have two different asymptotes going to the right as I go to infinity and going to the left as it approaches negative infinity. I can have different asymptotes. All right. Okay. The kicker here is that I'm either going to approach positive or negative infinity and then I get some numeric value. You can also make that infinity, right? As you approach infinity, you can also go to infinity. So it doesn't have to be just a specific number, but you can also just get infinity. I'm going to show this to you. So here is a visual representation of what we just talked about there. Let me scoot it down a bit. So here I have my graph as I approach infinity. I'm going to the right. My graph up here is approaching this value L. There's that horizontal asymptote that it's approaching and not going past, so I can approach L for that horizontal asymptote. As I'm approaching negative infinity, you can come down here and you've got this horizontal asymptote also at M. All right? So that's what could happen. You could, right? I mean, this is not the only option out there available. This is the concept. So a lot of times we talk about a specific concept and then you take that concept and you put it to whatever situation you have that you're going for. You could have something like a graph that comes like this, right? And then you've got your horizontal asymptote right here. A single horizontal asymptote if I'm approaching positive infinity, or if I'm approaching, going back in this direction, is x is approaching negative infinity, you're going to the same value. That's okay too, right? You can have the same going to the right or to the left. You can have, I don't know, there's lots of options out there. This is just the concept that you look at as I approach positive infinity or negative infinity, and then whatever you get out of that deal, that's how you know where your asymptotes are going to be, your horizontal ones. Okay, so let's do some examples here. Here is example 1. I want to evaluate the limits. So I have that's an A, contrary to what it looks like. I have the limit as x approaches negative infinity of 2 plus 10 over x squared. All right. Remember, back to your limit laws. The same limit laws apply always and forever. You take the limit of each piece and then you say what that is happening. Now look at what's going on here. The limit as I approach 2 is always just going to be 2. That's just that constant, right? So that never changes. However, look at what's happening here. If I'm approaching infinity, what happens to your fraction when the denominator gets super huge? Yeah, goes to 0, right? Think about this. if I have 1 over 50,000, super duper small, right? And the concept of a limit is I'm saying, what am I approaching? Not what is my final answer, but what am I approaching? You can't land on something specifically whenever you're talking about infinity. What am I getting arbitrarily close, right? That's always a terminology that's used with limits. Arbitrarily close. When my denominator goes to infinity and my numerator is the exact same, then that is getting closer and closer and closer to 0. And that's how my limit here is just a 2. All right. Okay. Oh, so here's the other thing. If I can look at this, I have as the limit as x approaches negative infinity, just, for fun, let's look at this and say, what is my limit as x approaches positive infinity? Same thing. Yes. So you still have the 2 because that's the constant. And whether I'm approaching positive or negative infinity, this is still going to be massively huge and take me to 0. So we can look at this and say our only asymptote here, our only horizontal asymptote, it's going, whether I'm going to positive or negative infinity, I'm going to the same place. So my horizontal asymptote here is 2. This problem's not specifically asking for that, but I just wanted to make the connection for you. Okay, let's do another one. Again, we're evaluating the limit. I'm taking the limit as x approaches infinity here of 5 plus the sine of x over the square root of x. The whole thing. Yeah, so 5 is 5, right? Because that's our very first one that we have, and so then that's good. But what did we talk about already in terms of sine? Squeeze theorem. Yes, I know you were saying that. I could feel it. I could feel you saying it. Squeeze theorem. So this is 5 plus, then this, we're going to squeeze this. All right, so I know that we're going to build up for our squeeze theorem. We're going to say -1 is less than or equal to sine of x, which is less than or equal to 1, right? Then, because I am dividing by this square root of x, you have to divide everything by the square root of x. Then you take your limit of each one of those pieces. So I'm really taking the limit here as x approaches infinity because that's what we start with here. So we're using the same value of -1 over the square root of x. Well, what did we say? When that denominator grows huge, the whole thing goes to 0. Same thing over here. The limit as x approaches infinity of 1 over the square root of x, still 0. So by the squeeze theorem, we know that the limit as x approaches infinity of the sine of x over the square root of x is also 0. Wow, my handwriting's getting worse and worse, isn't it? Stick with me. So because of this, we know that's a 0. So my whole limit here is a 5. Right? We can prove this with the squeeze theorem. But so then just remember the concept of a limit, and you're just looking at what you already know and you're pulling that off. This sine of x, the only place it's going to go is bounce between positive and -1. It's not going to get any bigger than that. Because I know that, this is going to grow infinitely. Now it's a square root, so it's not going to get there very fast, but it is going to grow infinitely. So as this grows infinitely, it will certainly surpass my positive or -1, and that's the other thing, it can go to 0. I'm saying this because, yes, we can prove this with the squeeze theorem. However, if you took this problem and you only showed this amount of work, I would take that all day long. All day long, I would take that. So yes, this is the actual proof as to how you can pull that off, but all you need is that piece. All right? Okay. I just want to make sure that we're good with that. Yes, this is the background behind it, but now that we know the background, we can use that and move forward. All right. Okay. Check this out. Limits at infinity of powers and polynomials. So we're just hitting the basics here. So our first one, if I take the limit as x approaches positive or negative infinity of x to the n, that's going to be infinity when n is even. Because think about it. If you have an even exponent, it doesn't matter what's happening there, right? It's always positive. All right? And so then we could break this up. The limit as x approaches positive infinity of x to the n is equal to infinity. And the limit as x approaches negative infinity of x to the n is equal to negative infinity when n is odd, right? Because if you have an even exponent, if you have an even exponent, it's always positive. But if you have an odd exponent, if you plug in a positive, you get positive. If you plug in a negative, you get negative, right? Okay, so positives and negatives. We're just using what we already know, previous information, into the current lesson so that we can move forward with it. Okay, check it out. The limit as x approaches either positive or negative infinity of 1 over x to the n is equal to 0. No matter what. I can approach positive infinity. I can approach negative infinity. N could be odd. N could be even. No one cares. It's back to the concept we just talked about. When your denominator grows super big, then the whole thing is going to go to 0, whether you're going towards 0 from the right or from the left. It doesn't matter. The whole thing is going to go towards 0. All right? Okay. Here's our last one. I'm going to take the limit as x approaches either positive or negative infinity of a polynomial. All right? So I can look at that and say, as x approaches positive or negative infinity of a sub n, x sub n, x to the n is equal to positive or negative infinity. Here's the thing. This is lead behavior. So your highest exponent and the value in front of it. All right. It depends if you're going for positive or negative. This depends on degree. If it's odd or even, right? If it's odd or even degree, that n, your degree is your n, right? Depends on your degree. If it's odd or even, and the sign of that leading coefficient. So you're talking about odd or even, squeezing this in, back up here with this concept. That's odd or even, depending on what's happening here. Then you could go to positive or negative infinity if this is odd. Now, if it's even, right, then this is always going to be an infinity. But if this is negative, you can still go to negative infinity, right? You're just looking at your signs. What's positive, what's negative as you multiply this leading coefficient together. All right? Okay, let's practice one here. If I have example 2a, we want to find the limits as we go to both positive and negative infinity. I want to take the limit as x approaches infinity here of 3x to the fourth minus 6x squared plus x minus 10. I'm also taking the limit as x approaches negative infinity of this exact same thing. All right, I'm going to scoot this down. So here's my first one. I am looking at the lead behavior because that's what this number 4 told us to do. So when I take my limit as x approaches positive infinity of a positive number here that I'm looking at of x to the fourth, and the fact that this is even, so it's always going to be a positive no matter what, this whole thing goes to positive infinity. All right, it's a polynomial. I know it's going to be infinite, and it goes to positive infinity. What if I'm looking at negative infinity? Again, the fact that this is an even exponent, I know that's going to be a positive infinity situation again. So a positive 3 times that positive infinity is going to take me to positive infinity. So this one, because I have a positive number in front and an even coefficient, it takes care of that. What if I have something like this? I have the limit as x approaches positive infinity of a negative 2x cubed plus 3x squared minus 12, and the limit as x approaches negative infinity of negative 2x cubed plus 3x squared minus 12. Right? Odd, so that is affected, and I have this negative in front. So the limit as x approaches positive infinity of negative 2x cubed. This is going to give me that negative number here times, because this is positive infinity, a positive. So a negative times a positive gives me that negative infinity. Do you see what's happening? Okay. So here, if I have the limit as x approaches negative infinity of that leading coefficient, again, I have this negative because it's just the number, but negative infinity with that negative exponent, I'm just going to put the negative there. That is how I come up with a negative times a negative gives me a positive infinity. So you're looking at your positive and negative values when you're talking about polynomials.